Our first speaker is Professor Eiji Nishibori from the University of Tsukuba. He's a leading expert in quantum crystallography. I will introduce short bio of Professor Nishibori. And Professor Nishibori is a full professor at the University of Tsukuba, and he has been the director of the Tsukuba Research Center for Energy Material Science since 2023. He earned his PhD in engineering from Nagoya University. His research focuses on quantum crystallography, synchrotron radiation science, and the development of innovative approaches for material science. He has received several awards for his contributions to crystallography and material science to date. So today, his talk is titled X-ray diffraction and scattering studies using advanced X-ray sources. So, Professor Nishibori, please.
Thank you very much for Harada-sensei. I'm Eiji Nishibori, University of Tsukuba. The title of my talk is X-ray diffraction and scattering studies using advanced X-ray sources. The meanings of advanced X-ray sources is the XFER at Sakura and the high energy pink beam, the relatively recently available at Spring 8. These are the contents of my today's talk. The first, I'd like to talk about two-color XFER pump and probe experiment for structural studies. The first, I talk about advanced techniques for experiment. The X-ray pump and probe using two-color XFER. The two-color hard X-ray XFER were available at Sakura for more than 10 years. This slide shows the mechanisms of how to make a two-color XFER. In this study, we use two-color XFER for pump X-ray and probe X-rays. The two-color XFER were created and the first section of one undulator and second section of undulator. The electron bunch were going through in between this path. The time delay are created by using this scan. We can use the high quality, the same quality X-ray from common X-ray bunch for pump and probe experiment. The target of this study is non-thermal melting. This is ultra-fast melting found in the semiconductors. This phenomenon itself was observed early 1990s. Then many studies have been carried out. The non-thermal melting is the femtosecond laser irradiated materials. Then the reflectivity changes within 1 picosecond. But normal melting, it takes more than 1 picosecond due to the atomic movement. The next slide shows the explanation of the thermal and non-thermal melting. In the case of thermal melting, laser excited electrons. The electron interact phonons. Then the phonon-phonon interaction causes melting. It takes more than 1 femtosecond. In the case of non-thermal melting, the melting will happen within 1 picosecond. What happened in this non-thermal melting? To reveal the atomic scale mechanism of non-thermal melting, we performed the pump and probe experiment at Sakura for charge density study. This work was performed by international collaboration between RIKEN at Spring 8 site and CFER at DEIJI. the purpose of this study is structure changes of atomic and electronic scale in non-thermal melting. Our role is a suggestion of experimental conditions and data analysis. This slide shows the sample of the first study is diamond. This slide shows how to determine the experimental conditions. To reveal charge density level structure, we used the multiple modeling. In this case, we have to determine the 7 parameters, as shown here. But the available reflection is limited due to experiment is not so easy. So how many reflections we required reality. So we investigate how many reflections are required for this study. This is the structural refinement using the no chemical bonding contributions. This is a full parameter refinement. We found 4 parameters required to express the chemical bonding. So to determine 4 parameters, we need 5 Bragg reflections. So we did experiment to measure at least 5 Bragg reflections. The experiment carried out at BL3 at Sakura. This is a photo of experiment. We used 3 detectors. This is pump X-ray was this energy, and probe X-ray was this energy. And we measured 5 Bragg reflections with this time delays. This slide shows the one-dimensional diffraction data. As you can see, intensity decreases with increasing delay time. But I surprised this at first to see this result, because the normal melting with lattice expansion, so peak position should shift. But in this case, there is no peak shift. This is non-thermal melting, evidence of non-thermal melting. We analyzed this data. This is a change of relative intensities from 0.5 femtosecond to 100 femtosecond. As you can see, we can clearly recognize the change from before 20 femtosecond and after 20 femtosecond. So we did charge density study using this data. At first, we show this region, what happened. We show thermal displacement parameter. This slide shows the thermal displacement parameter of diamond. As you can see, before 20 femtosecond, the values are almost constant. This indicates there is no change of the structure itself. Then, after 20 femtosecond, the values are rapidly increase with increasing the time. This slope is almost consistent with free carbon gas. So the sample disappears after XFL irradiation. So it behaves as a free carbon gas. So what happened before 20 femtoseconds? We did charge density study. This is parameters for multiple refinement. This is a balanced charge density of 0 femtoseconds. This is 0.5 femtosecond. So this directional bonding decreases dramatically. And 5 femtosecond almost completely disappears. The 10 femtosecond, 20 femtosecond almost same, and 35, 50, and 75 are smeared. So we observed it is found that the bond break will happen within 5 femtoseconds. After 50 femtoseconds, the charge density is smeared. Finally, our observation was theoretically explained by theoretical calculation at CFAL. This is the first work of non-thermal melting. We also did similar works different samples. In this case, we use alumina. Alumina have two positional parameters. So the question is, what happened? The positional parameter changed or not changed in non-thermal melting? In this case, we did little bit refinement of these time-delayed data. As you can see, the fitting self-satisfactory. In this case, there is also almost no change of lattice constants. So this slide shows the time dependence of the structure. This is the structure of alumina. Silver is aluminum, and lead is oxygen. This is at the time dependence of atomic coordinate. As you can see, below 20 femtosecond, there is almost no change within experimental error. But after 20 femtosecond, the coordinate of aluminum changed gradually. This is a plot of the interatomic distances of the aluminum. Aluminum is red, and aluminum oxygen is blue. We observed directional displacement in non-thermal process without lattice constant change. Finally, the theoretical simulation confirmed that these directional displacement originate from non-thermal process driven by electron excitation and relaxation. Okay, let's move to the next topics. I briefly talk about our recent XFL work, XFL PDF, and SFX for small molecule for time-resolved atomic scale structure study. This is collaboration between Professor Bo Iversen group at Aarhus University, Denmark. This slide shows our international collaboration between Aarhus University. I collaborate with him for more than 25 years. This is a photo at Denmark, and this is a photo at Sakura. We performed the many collaboration grants from JSPS and Kakenhi grant and inside the university grants. One of the important international collaboration work is XFL for material science. I think this is the first PDF work in the world by using XFL. In this case, we observed Hafnium nanoparticles. This is diffraction data, and this is a PDF. As you can see, we can determine the particle size from this PDF. In this study, we demonstrate the potential for femtosecond PDF studies of amorphous and disordered materials. Another international collaboration is serial femtosecond crystallography for small molecule. This topic has attracted attention during past several years. This is the first papers from US group, and this is second paper. Maybe Ishikawa sensei is the co-author of these papers. And my group, we are author of the third papers. Now we are submitted our newest results. I hope we will present our new results near future. Finally, I talk about use of advanced source for material science, the 100 keV pink beam, which is recently available at Spring 8 for amorphous studies. This is a collaboration between Dr. Shuai Wei at Aarhus University and Professor Kono at Kwansei Gakuin University. The target of this work is phase change material, so-called PCM, and to reveal the polymorphic phase transition is the main topic of this talk. The phase change material is attracted attentions the reversible and rapid switching between amorphous to crystalline phase can be used to store information in device. So these type of material attracted attention. Recently, the phase transition from one amorphous to another amorphous states were observed under high pressure. But the atomic scale mechanism is completely unknown. Relatively recently, this paper reported the liquid-to-liquid phase transition of supercooled PCM. In this case, origin of phase transition is this pious-like distortion, as shown here. This structure of this octahedra changed to like this. By changing the structure, we observed the pre-peak at here. So the main question of this work is the mechanism of amorphous to amorphous phase transition is the same as that of this liquid-liquid phase transitions. But to reveal this structure origin, we have to measure the high-quality PDF under high pressure. So in this study, we used the high-flux 100 keV X-ray beam, since the high-pressure experiment have a limitation because we have to use high-pressure cell. So the measured angle is limited by the window of the cell. So in this study, we use 100 keV pink beam, and this system developed by Professor Kono at Kansai Gakuin University. This is group members. The samples are germanium selenide and germanium telluride. We measured high-pressure diffraction data of these materials. This slide shows the X-ray scattering data of germanium selenide and germanium telluride. As you can see, at ambient pressure, we observed pre-peak. So there is the pious-like distortion exists even at ambient pressure. This peak, intensity of this peak decreases with increasing the pressure. So it is found that applying the pressure, the high pressure phase, pious distortion disappears. To determine the phase transition pressure, we analyze the PDF from diffraction data. These are PDF of germanium selenide and germanium telluride. We observed very clear PDF by using the high resolution data, high reciprocal resolution data. We investigate the peak position of this peak. The tendency are clearly changed at here and at here. So we uniquely determined the phase transition pressure from this high resolution PDF. In this study, we revealed the polymorphic transition in germanium telluride and germanium selenide is typified by the suppression of pious-like distortion in the atomic arrangement. So in the case of supercooled liquid, low temperature phase have pious-like distortion. In the case of high temperature study, the low pressure phase have pious-like distortion. So we believe there is some border in here, around here. To reveal this border, we plan to do the next experiment. We have a plan for next experiment. Now we are continuing to do this work. In this talk, I present 3 topics using the XFEL and high energy X-ray at Spring 8. This is a summary of my talk. The worldwide development advanced synchrotron and X-ray sources enables visualization of atomic scale structure in unexplored regions. I think in these works presented here is all of these works are international collaboration. So international collaboration with researchers sharing similar goals and environment is highly effective. The enhancing access models such as international collaboration-based utilization will improve opportunities for cutting-edge research. That's all. Thank you for your attention.